Hello students, welcome to EPG Pathshala. I am Dr. Ajit Kumar Mahapatro from the Department of Physics and Astrophysics, University of Delhi, Delhi, India. Today we are going to discuss about the module Rutherford backscattering part 3. It comes from the paper Characterization Techniques for Material 2. From this module, the students may get to know about the following. First, we will learn about the depth scale for elemental analysis. Second, we will go for learn about the surface energy and mean energy approximation. And in the last, we will study the spectrum height for an element. The quantification of atomic composition, the yield ratio of atoms scattered from the surface of the sample needs to be compared with energy, and at a certain depth of the dependence of the energy width of the detector channel on backscattered energy. Ions, when travel through a solid, loses their energy by screened Coulomb collision with the target nuclei and free target electrons. We already know that during scattering, the nuclear energy loss is approximately 3 orders of magnitude smaller than the electronic energy loss. Energy loss of nuclei is mainly of interest in ion implantation and spotter etching techniques like secondary ion mass spectrometry, referred as SIMS, whereas electronic interactions are the dominant mechanism for energy loss in the ion scattering analysis techniques. Thus, one can selectively choose the incident beam species, energy and materials composition to get the desired result. As an energetic ion moves through matter, there is a loss of energy because of the Coulomb force acting on the electrons from the target atom. The passing of charged particle produces interaction which is Coulombic in nature. Since the electron has light mass, it doesn't affect the path of incident ions. This section describes the relation between the energy of the detected particle and the depth at which the backscattering event occurs in a monoisotropic elemental sample. Various approximations were taken into account and are mathematically derived for the quantitative analysis. Depth scale analysis is important to get knowledge on the number atoms participating in the backscattering process. The depth scale for an elemental sample. The figure 1 shows the energy relation of an incident particle before and after scattering. Let the energy E0 be the energy of incident particle, energy immediately before scattering at a depth x is E, and E1 be the energy of the particle emerging from the surface. It should be noted that the incident beam is smaller than the target. The incident particle, scattered particle and the normal to the surface of the sample lie in one plane. In the laboratory frame of reference, it is given by theta is equal to 180 degree minus theta 1 plus theta 2, where theta 1 and theta 2 are the angles between the normal and the direction of the incident beam and the scattered particle respectively. Theta 1 and theta 2 are positive if they lie in the same side of the plane. We can relate the energy E with x by x divided by cos theta 1 is equal to minus integration going from E0 to E dE divided by dE by dx. Negative sign arises because E is less than E0 and dE by dx is a positive quantity. Similarly, the outward path related by the equation x divided by cos theta 2 is equal to minus integration from the kinetic energy to E1 dE divided by d by dx. A graphical interpretation of these two equations is given in figure 2 that represents the energy loss in a sample in mean energy and surface energy approximations. Part A shows dE by dx as a function of energy as a light line. The heavy segments given in dE by dx values for the inward path from E0 to E and for the outward path from kinetic energy to E1. The difference E0 minus E is the energy loss along the inward path delta E in. Similarly, the kinetic energy minus E1 is the energy loss along the outward path delta E out. Mathematical formulations of energy loss factor represented as S or stopping cross section epsilon if one assumes a constant value for dE by dx along the inward and outward paths, the two integrals can be written as E is equal to E0 minus x divided by cos theta 1 dE by dx at in and E1 is equal to kinetic energy minus x divided by cos theta 2 dE by dx at out, where these subscripts in and out refer to the constant values of dE by dx along the inward and outward paths. By eliminating E from these two equations, we have kinetic energy 0 minus E1 is equal to k divided by cos theta 1 dE by dx of inward path plus 1 divided by cos theta 2 dE by dx at outward path whole multiplied by x. The energy Ke0 is the edge of the backscattering spectrum and corresponds to the energy of particles scattered from atoms at the surface of the target. The energy Ex is the measured value of a particle scattered from an atom at depth x. If one introduces the symbol delta E for the energy difference between Ex and Ke0, that is delta E is equal to kinetic energy 0 minus E1, delta E is equal to S multiplied by X, and S is then energy factor or S factor, and can be written as S is equal to K divided by cos theta 1 dE by dx at inward path plus 1 divided by cos theta 2 dE by dx at outward path whole multiplied by x. In terms of stopping cross section or epsilon factor, this can also be written as epsilon is equal to K divided by cos theta 1 epsilon inward path plus 1 divided by cos theta 2 epsilon at outward path. If the energy loss is constant both outside and inside of the sample, the energy delta E is linearly related to the depth x, which can be written as delta E is equal to S times x, represented in the schematic diagram figure 3. Figure 4 depicts graphically the relation between energy loss factor S and actual depth x at which backscattering occurs for a given energy loss delta E. It is clear from the graph that it is not exactly linear. Figure 4 is the schematic relation between the energy loss delta E and the depth x at which backscattering occurs, and the relation delta E is equal to A times E is equal to S times x is exact at one depth. The symbol S0 refers to the surface energy approximation. The approximation to S and epsilon. Surface energy approximation for these regions near to the surface x is small and the incident energy also remains constant. Hence, both dE by dx and is at inward and outward paths are taken at kinetic energy 0. In the surface energy approximations, this equation can be written as S0 is equal to K divided by cos theta 1 dE by dx at E0 plus 1 divided by cos theta 2 dE by dx at K E0, and epsilon 0 is equal to K divided by cos theta 1 epsilon, which is a function of E0, plus 1 divided by cos theta 2 dE by dx of epsilon is a function of Ke0, where epsilon 0 and Ke0 are evaluated at the initial energy point. Mean energy approximation. The surface energy approximation is no longer valid when the path length becomes appreciable. As a result, the surface approximation degrades. A better approximation can be obtained by selecting a constant value of dE by dx or epsilon at an energy E intermediate to that which the particle has at the endpoints of each track, and S0 can be written as S0 is equal to K divided by cos theta 1 dE by dx at E in bar plus 1 cos theta 2 dE by dx at E out bar, and epsilon 0 is equal to K divided by cos theta 1 epsilon is a function of E in bar plus 1 divided by cos theta 2 dE by dx epsilon is a function of E out bar. In the mean energy approximation, one assumes that E in bar is equal to half multiplied by E plus E0. E out bar is equal to half kinetic energy Ke plus E1, or E in bar is equivalent to E0 minus 1/4 of delta E, and E out bar is equivalent to E10 plus 1/4 delta E, where delta E is equal to Ke0 minus E1. Now, let us study about the energy spectrum for a sample and height determination. We will see in this section the relation between the height of the energy and the number of scattering centers per unit area within the sample where backscattering occurs. In the remaining sections of this chapter, only stopping cross sections epsilon and stopping cross section factors will be used. There is a functional dependence between the energy axis of a backscattering spectrum and the depth below the surface of a sample. Each energy width epsilon of a channel I in the multi-channel analyzer is backscattering events recorded in channel I of thickness tau I. The number of counts Hi in channel I is dependent on two factors, including the thickness of the slab and the number of scattering centers in that cross section. The main goal is to find out the energy, width S, and the position E1I of channel I in the energy spectrum indicated in figure 5 by correlating the number of counts Ht to the number of scattering centers per unit area N tau I in the slab of thickness tau at depth xi, which corresponds to the energy of a beam of normal incidence. The total number of particles detected in channel I can be Hi is equal to sigma, which is a function of Ei, omega q n tau I divided by cos theta 1. The schematic diagram showing the relation between the slab I at the depth xi and energy E1I is represented in the figure. In the equation Hi, the sigma Ei is the differential cross section at energy Ei, omega is the solid angle, q is the total number of sample incident on the surface. This is true if the incident particle is normal to the target surface, which would give the total number of backscattering atoms of the sample. If there is a tilt in the incident particle from the normal of the surface with angle theta 1, then the equation can be written as Hi is equal to sigma Ei omega q n tau I divided by cos theta 1. Spectrum height for a scattering from the top layer. Figure 6 gives a schematic diagram of the backscattering processes from the top surface of the sample and the spectrum resulting from it. The notation we have taken for the near surface region is H0 and tau 0 instead of Hi and tau I for regions within the sample. Schematics of the backscattering process in the surface region of a sample consisting of a monoisotopic element, and the resulting spectrum is given in the right. Here H0 is given by H0 is equal to sigma E0 omega q zeta divided by epsilon 0 cos theta 1. This equation states that the height of the energy spectrum at the surface is directly proportional to q, the total number of incident particles on the sample, sigma E0, the average differential scattering cross section of the sample at the incident energy E0, omega is the solid angle spanned by detector aperture, zeta is the energy width of a channel, epsilon 0 cos theta 1 inverse is the inverse of the stopping cross section factor evaluated at the surface for a given scattering geometry multiplied by the cosine of the angle of incidence of the beam against the sample normal. Spectrum height for scattering at depth. The significance of depth profiling is to relate a spectrum height Hi to a slab of material with thickness tau I and number of atoms per unit area n tau I at depth xi. The height can be written as Hi is equal to sigma Ei omega q n tau I divided by cos theta 1. The cross section sigma is evaluated at the energy Ei of the projectile immediately before scattering at depth xi. The amount of material n tau I is defined by the energy width zeta such that the particles backscattered from the slab will emerge from the sample with energies between E1I and E1I minus zeta. It would be wrong to conclude, therefore, that the energy width zeta of these particles immediately after scattering is also S. The reason is that particles with slightly different energies after scattering at x undergoes slightly different energy losses on their outward path. H, the function of E1, can be written as sigma E omega q zeta divided by epsilon is a function of E cos theta 1 multiplied by epsilon ke epsilon e raised epsilon is a function of kinetic energy ke divided by epsilon is a function of E1. Incident beam penetrates the surface energy of the projectiles decreases. As a result, the scattering cross-section sigma increases. This effect tends to increase the yield Hi with decreasing energy E1 of the detected particles. On the other hand, the stopping cross-section also varies with E. In general, this dependence is not as strong as that for sigma E, but epsilon can either increase or decrease with decreasing the values of E. Consequently, the effect of the change in epsilon on the backscattering yield may either enhance or counteract the effect of the change in sigma. The depth scale for a homogeneous solid containing more than one element or a compound sample. In this section, we shall discuss the backscattering spectrum of a sample composed of a homogeneous mixture of several elements. For simplicity, we denote the materials as a compound sample, although it could be either a mixture or a chemical compound. This case differs from that of the monoisotopic elemental sample considered thus in two segment ways. First, as the probing particle penetrates the film, they lose energy as a result of interactions with more than one element. Consequently, the stopping cross-section depends on the composition of the sample. Second, when the probing particles with energy E are scattered at a specific depth within the sample, the value of the kinematic factor K and the scattering cross-section sigma will depend on the particular mass, which is atomic number, of the atom they strike. Since the stopping cross-section varies with energy, the energy that the particles lose along identical outward tracks also depends on the atom struck in the scattering collision. For a compound sample, the yield of the backscattering spectrum and the energy to depth conversion thus depends on the element struck in the collision. All counts generated by backscattering from a given element constitute the signal of this element in the spectrum. A particle penetrating the sample to a depth x undergoes an energy loss given by delta E in is equal to nx superscript AB divided by cos theta 1 multiplied by epsilon in superscript of AB, where n superscript AB is the number of molecules A, M, B, N for unit volume. The energy loss delta E out along the outgoing path depends on the collision parameter. We have delta EA is equal to epsilon subscript A superscript AB multiplied by N with a subscript X and superscript of AB. Epsilon subscript A superscript AB is equal to Ka divided by cos theta 1 epsilon in superscript AB plus 1 divided by cos theta 2 times epsilon out subscript A and superscript AB, where delta EB can be written as epsilon subscript B superscript AB multiplied by nx superscript AB, and epsilon subscript B and superscript AB can be written as Kp divided by cos theta 2 epsilon in superscript AB plus cos theta 2 epsilon out subscript B and superscript AB. So students, let us summarize what we have learned in this module. In this section, we got the knowledge of depth scale analysis with the help of energy of the detected particle, the relation between the energy loss factor S and the actual depth x at which backscattering occurs for a given energy loss of delta E was calculated and shown graphically, which states that it is not a linear. Two approximations were considered, one surface energy approximation and the other mean energy approximations. When the length scale is appropriate, surface energy approximation fails. The spectrum height was calculated, which also depends on solid angle, scattering cross section and thickness of the material. By using the approximations described in this module, we got the knowledge on the calculation of height of a spectrum of an element and compound film both on the surface and at a certain distance from the surface of the sample. Thank you.